Hi, and thanks for tuning in. It's surprising how many people still think gamma spectroscopy is an out of reach science, but that's no longer the case. With sound card spectrometers, anyone interested in science or interested in learning about the atoms, about the inner workings of things, gamma spectroscopy is more than affordable. I'm going to do a demonstration today using the GS Pro V5, which is a USB spectrometer, and I'm going to use a scintillation detector, which is a GS1515 CSI scintillation detector with a 1.5 inch crystal. Now, I'm going to use for this demonstration our software, which is free, open source. It's called Impulse, and you'll be amazed what you can do with this simple equipment and Impulse software. This video takes about 20 minutes, so feel free to speed it up if you think it goes a bit too slow, but I'll be showing most of the features in the software, and I'll be leaving links in the description so you can find your way around. Thanks, and let's go. This is going to be a quick, or maybe not so quick, demonstration of Impulse gamma spectrometry software. This software is free and open source, and you can download it from GitHub. This software works with sound card spectrometers like the Gammaspectacular, and it also works with serial devices like the atom spectra devices. But for this particular demonstration, I will be demonstrating the sound card device. And there are some differences in the screens. So when you connect a sound card device, this is the screen that will come up when you launch Impulse. Impulse will work on Macintosh, Windows and Linux machines. So it truly is a cross-platform program, and being open source means that if you are familiar with Python code, you can go into the code and edit those areas that you like to improve, and feel free to make a branch of the program and suggest improvements, and we might take those up in future versions. All right, let's get into it. When you launch Impulse, it automatically opens up in your default browser, and it opens up to this page here, which is the one where you select your device. And the program is designed in tabs, and all your settings and all the different functions are on various tabs. So we're going to start here on the Devices tab, which is where you select your device. So I have now connected my device, and it comes up here in the Devices index as USB audio codec. This is the name given to the Gammaspectacular GS Pro model. But if you're using a sound card on your PC, you might have a different sound card name over here, but that's perfectly fine. Now, the next step is to select your sample rate. Now, many sound cards sample at 48 kilohertz by default, but since we're reading the sound card as an audio stream, we can in fact oversample the sound card. And you can choose a sample rate which is faster than your actual sound card and achieve a better result. So in my case, I'm using 192 kilohertz. I could go to 384 kilohertz, but I prefer 192 kilohertz as it puts less strain on the CPU, and it's easier to process the pulses. The next decision we have to make is the sample size. So this is related to the sample rate. At a high sample rate, you need a longer sample size, and at a lower sample rate, you need a shorter sample size. So 192 kilohertz, I have chosen 31 samples, which gives me a sample length of about 161 microseconds, and comes up with a little warning up here in the corner. So this is the time it takes from the beginning of the pulse sampling until the end of the pulse sampling. And the 31 dots mentioned here, these are the little dots which indicate the individual samples along this pulse shape. The next thing we're going to do is we're going to determine how many pulses we want to sample. And here you can see it's been set to 500. So what that means is from the audio stream, it collects 500 pulses, creates a sum of all the pulses, and then finds the mean average, which is what will be plotted here on the screen. So if I now click Capture Pulse Shape and click the button here, you will see that that is now collecting a pulse shape, and there it is, it has updated. You might not see that it changed much because I'm using the same device as my previous one. So this is a fresh pulse shape now, and it is beautifully rendered on the screen there. Now I have a little function here where I can offset the pulse peak. In some cases that might be interesting. So if I offset the peak here and collect another pulse shape, we can see that when it comes back, we now have an offset peak. And for some spectrometers that might work better, but for my case, a simple centered peak works perfectly fine. The next field over here is the distortion curve. Now this distortion curve is interesting because we're using it as a filter on the next page where we're going to do our gamma spectrum. So what we refer to as a distorted pulse is a pulse that does not follow this exact pulse shape. So we do a complex calculation involving the root mean squares of every sample, and we subtract the mean pulse shape, which is this shape that we have collected here. So in the event that the pulses coming in are identical to the mean pulse, the distortion would be 0. The more the pulse deviates from the mean, the higher the distortion. So let's run a quick distortion curve and see what comes out. And typically it looks like this, where you get a curve which looks like a hockey stick. So here you can see the distortion is relatively small until this point here where it suddenly goes vertical. And that is really where we want to discriminate and say, hey, we don't really want the C pulses, which are heavily distorted, so we discriminate at this point. So we're going to put that number in on the next page when we go to do our histogram. Let's look at tab number 2, your histogram tab. We have here 2 buttons, start and stop, self-explanatory, and underneath these 2 buttons we have the stop condition, max counts and max seconds. So either or, once your spectrum has reached the maximum counts or the maximum seconds, the recording will stop. Okay, this allows you to repeat an experiment several times and with the same number of counts or the same number of seconds. In the next column here, we have an option to choose an existing spectrum if you wish to view one of your previously recorded spectrum, or to create a new file name. So let's do it. Let's create a spectrum called my uranium spectrum. Okay, and we arbitrarily give that 4092 channels. Any arbitrary number will work. And the pitch per channel is 2, and we'll later on see that this is about the right pitch for the to see the whole spectrum within the screen. And we call it the bin size, but it's essentially the pitch of the channel. Lower limit discriminator is an arbitrary number. It's set to 60, and that's to discriminate the electronic noise that might come from the spectrometer or the ripple on the baseline. We don't want to see that in our spectrum because it will generate thousands of counts which are not related to gamma. So I've set that to 60, and the shape tolerance that we took from the previous page, the little graph that we did on the shape tolerance, we set that to 6,000, or we can set it a bit above. We can set it to 10,000 to make sure we capture all the pulses that we want. And we've set the interval the update interval to 1 second. So that means it updates the screen at 1 hertz. And that's pretty much all we have to do to start recording our spectrum. So yeah, let's hit start and see what happens. And there we go. And you can see immediately the audio stream starts coming into the computer, and each pulse is measured against the mean and the pulse shape and filtered accordingly. And the ones that pass the tolerance filter get rendered on the screen. So each one of these 4096 channels along here have counts in them, which representing how many pulses were counted with that particular pulse height. And as you can see, it's pretty quick. It starts counting straight away. We're already up to 24,000 pulses. Now in the next column here we have a few, we might skip one column and do this one first. Here we have some toggle switches. One is very common in gamma spectrometers, and that's to represent the spectrum in log scale. So when we turn that on, we get a log representation of the spectrum, and this is what you often see when gamma spectra are represented on an image. We also have the option here to represent the spectrum as energy by bin. This is also a way to enhance the high end of the spectrum. All it does, it simply takes the bin number and multiplies it by the counts. So if the bin number is low, the multiplier is low. If the bin number is high, the multiplier is high. So it enhances the counts on the right-hand side of your spectrum. I think it's quite handy. Next one is calibration. Okay, now calibration is on Impulse a second order polynomial. So we calibrate with 3 channels. So if you take a channel over here of a known peak, let's say the first one there, and you say, okay, that channel number is 98. It's a 98, and that we know that that happens to be an X-ray at 80 kilo electron volts. Great. Next channel you might pick up 792, and we know that that's a 609 peak. And we also know this one over here, if I show that in a little bit more enhanced, this one over here is the thorium at 2614. So that's in about bin 3530 at 2614. So when I turn on calibration, you will see the x-axis now changes, and we now have the approximately right calibration numbers in these bins. Underneath here there's a feature called Peak Finder. Okay, that can be quite handy because it will automatically identify some peaks. And as you can see, it looks a bit messy now because the spectrum has not been running for very long. But once the spectrum has been going for a while and it becomes smoother, you will see that these peaks become more enhanced and that these numbers become more accurate. We can turn that off again. Let me just grab that and turn that off. And next we have a feature here called the Gaussian. Now this is an interesting calculation where it calculates the Gaussian peak, and it enhances the roughness of the background spectrum here, or the real spectrum, and pulls out the peaks so that we can see them more pronounced. You will see that this is also a function when we have the calibration on. It uses the Gaussian peak together with the calibration to suggest isotopes. So we have a little function here where you can press the button, isotope flags on, and now it will actually find all those peaks and it will suggest which isotopes might be in those. So this could be helpful if you have an unknown peak and you're trying to find the isotope which is generating that peak. It might be one of these suggested here in these flags. But remember, with gamma spectroscopy, it's not always that simple, because some of the peaks that you see in your spectrum may also be as a result of backscatter or some peaks or other issues that are created by the fact that there is a number of gamma rays in your spectrum. So that's pretty much the functions on this page. There are also a couple of other things I didn't mention. Over here we have an export to CSV. So if you have another program that you want to analyze your spectrum in that prefers a CSV file, you can now take your spectrum and you can export that to CSV. And another useful feature over here is the comparison spectrum. Okay, it allows you to compare a previously recorded spectrum with the current spectrum, and also to subtract the previously recorded spectrum. So this is particularly useful for subtracting background. I don't have a background spectrum recorder at the moment, so if I just use something else that was recorded, which is a previous recording of a similar spectrum, I can show you how that overlays the first spectrum. And if I switch to toggle switch to subtract comparison, it actually does a deduction, and then what you get is the net difference of the two spectra. In this case it doesn't make much sense, but if you have a background spectrum, I think you will find it very useful. Last but not least, there's a little field over here where you can write some spectrum notes. So I could write here, this is a test spectrum for my video. Okay, and this will get saved along with your spectrum data in Impulse data in your home folder. Yeah, that's about it. And there is one more thing here which we shall get to, and that is this button here which says Publish Spectrum. Now, this is a feature where you can share your spectra with other scientists using Impulse. I think it's a great feature because the more spectra we can see, the better we are at identifying peaks in our spectrum. So I strongly encourage you to share your spectra, particularly those spectra which are good and that you have calibrated properly. Share them up to the server, and that'll allow other scientists to see your work, and you will also be allowed to see other scientists' work on the same matter. And when you share this spectra, it gets pushed up to the repository, which is on tab number 5. And here you can see there's 220 spectra here, which has already been shared and that you have the privilege of seeing because you're using Impulse. Great idea. There is, however, one caveat, and that is before you are able to upload your spectrum, you must complete My Details on tab 0, which contains your name and address and email and website and all those details, and you also have to request an API. However, we give you complete control over your privacy. So on the right hand side here, there's a number of toggle switches which allow you to turn fields off that you don't want to be visible to the public. But I do recommend you use your first and last name and probably your institution and city and country, but I suggest you probably switch off the email address and phone number if you don't want to be contacted. But great feature, and here you have control over your spectra. So should you happen to accidentally upload a spectrum which is not correct or which you want to redo, you have the option here to delete it or download it and look at it again. So great feature, and I really recommend you sign up and participate in that as well. All right, well, that was pretty much it for tab 2. As you can see, our spectrum is still running here, and it's looking better and better as time goes on, and you will see it become smoother over time. So let's move on and have a look at tab number 3. Okay, we're on tab number 3. And what is tab number 3? Well, appropriately, this is a 3D histogram. Okay, this is a histogram that creates a new column every X number of seconds, whatever the interval is set to. And in this case, I'll keep it to 1 second just to show what we're doing here. And here we have the same button, start and stop, with the stop criteria. And we can give this a new name. So let's call this a 3D test spectrum, like that. And the calibration numbers actually come from the previous page, so I'm not going to worry about calibrating it at this stage. Yeah, just let's hit start and see what it does. Okay, here you can see that it starts building this 3D histogram, which is quite interesting for any spectrum that might change over time. You might be surveying an area, or you might be doing some well logging where you're lowering a detector into the well, and you'll see a difference over time. So yeah, it's up to your imagination what you use this spectrum for, but it can be very useful and interesting. But just be aware that because it's a 3D spectrum and it records an entire spectrum every second, you can end up with very large file sizes, which might be a problem rendering on the screen at some point. So if you're planning on recording a very long spectrum spanning several hours, I recommend increasing the interval size so that you don't get too many channels along the time axis. So you could set it to update every once a minute, for instance, and then you could let it run for hours. And you'll also get a more accurate spectrum because each channel will have more counts in it. So great little feature. Have a play with it and see what you can do with the 3D spectrum. I'm sure you can think of something useful. And finally, we've seen the repository, so let's move on to the last tab, which is tab number 6. Here we have Impulse version 2 manual. If there's a function that you don't quite understand or that you'd like to know a little bit more about, go to tab number 6 and find the function that you're questioning, and you can read a brief description of what that function does. On this page you will also find an option to change the background. I have a few options there for you. And finally, the exit button. As this program runs on Python, it is important to use the exit button to quit, because it closes Python and prevents Python running 2 instances at the same time. That's it. That's all, folks. Thanks for watching.